So here we are, assignment 3, number 1. And for all the assignment in the lab, we have two basic relationships that we're going to be working with. One is the definition of flux, and the other is Gauss's law. Those are two different things. See if you can write them down. Here they are. These will be the two tools or relationships or equations that we work with. This is the definition of flux. For most simple cases where E is constant and the area is flat and the angle remains constant, it'll just be E times A times the cosine of theta. The integral allows us to deal with situations where either the field or the direction of the field or the area element changes direction over a surface. Okay, so that's the definition of flux. Conceptually, it's the amount of field that passes through a surface, and visually, it's the number of field lines. So you can estimate it as the number of field lines that passes through a surface. The relationship between flux through a closed surface, which would be calculated this way, right? This is a double integral over an area closed surface of E dot dA. That's flux over a closed surface. It is equal to the charge inside divided by epsilon naught. That's Gauss's law. So when you see this circle, you see how many field lines? Looks like 20 lines. So 20 lines pass through this surface. 20 lines pass through this larger circle or spherical surface, and 20 lines pass through this square or cube, if you think of it in 3 dimensions. So these are all different surfaces, but they all have the same flux. Why? Because the same amount of field passes through them. Why? Because they all enclose the same amount of charge. There's a positive charge here that we're representing with 20 field lines. And so whether we look at this surface, or this surface, we see 20 field lines coming out. Field lines coming out means there has to be a positive charge inside. Okay, so now let's solve the problem. Calculate the electric flux through the inner sphere. There's 2 ways we can do that. The easy way is to use Gauss's law. We just take the charge, 8.96 nanocoulombs, and divide it by epsilon naught, and that will be the flux, the total flux through that inner sphere. It will also be the total flux through the bigger sphere. It will also be the total flux. Why? Because the Q inside is the same, or visually the number of field lines is the same. So all you got to do is put the 8.96 times 10 to the minus 9 here, and the 8.854 times 10 to the minus 12 here with the units. Do the calculations, and it will come out, you do need the units, it will come out with, let me just show you that. So there it is, the numbers with the units. You see one of the coulombs cancels, end up with newtons per coulomb times meter squared. That's field times area, and I left 4 significant figures. Strictly speaking, it should be 1020 because you should round it to 3 because of this, but you do have to put the units in the box. Okay, number 2, same thing, only we have a different charge, but the same setup. And so the flux, calculate the flux through one face of the cube. So we're imagining it a 3-dimensional cube, right? So there were 6 faces. So the flux through the cube, we're going to get it the same way. Q inside divided by epsilon naught, that'll be the total flux. But since it's a cube, and since it's at the center, the flux will come out evenly through all 6 faces. So you just need to take 1/6 of whatever it is that you calculate for the flux using Gauss's law. Another very similar problem. So once again, we'll use Gauss's law. We have the charge, which is negative. So you see the field lines are going in. We wouldn't even need to see the charge. Since field lines go in, it would have to be negative. And we have another arrangement with dimensions given. And it says find the flux through the middle sphere. Well, if you remember from the last one and you understand this, the number of field lines, whatever it is, it looks like more than 20 now. The number of field lines that passes through this sphere is the same as the number of field lines that pass through this sphere, is the same as the number of field lines that pass through the box. So the flux is the same. Why is it the same? Because the number of field lines is the same, but really the reason is because the charge enclosed is the same. So the flux through the middle sphere, it doesn't matter which sphere, you just take Q inside divided by epsilon naught, and the flux will be going in negative. So make sure you get the right sign and make sure you put the units. Same, very similar situation again, only you have a different charge, negative charge again. Same arrangement, this time you're finding the flux through one face of the cube. You know how to do that. It's going to be 1/6 of the total flux. Okay, read the problem carefully. The cube lines up with the axes, and we're given this as the field. So it's a uniform field, right? The electric field in the region is one number, so it has to be a uniform field. So do you know how to draw that? Do you know how to visualize that? It's important that you can visualize it. So that's what it looks like, a uniform electric field in the J hat direction. That's up along the y-axis. The lines are all evenly spaced. It's uniform. It would be, we talked about this before, it would be as if we placed this cube between two charged plates, where the lower charge were positive and the upper charge were negative, and it's in a uniform field. So that's just how to imagine what would cause it. And so from this, if you can visualize it correctly, the field enters through the underside that we can't see, and it leaves through this top side. And it doesn't pass through any of those four faces, right? Because it just goes right along the face, parallel to the face, so it doesn't enter. So it only enters at the bottom, leaves at the top. The net flux through the cube is 0. And why is that? Because there's no charge inside. Every field line that goes in comes out. So there's no source, positive charge, or sink of field lines, which would be a negative charge. So the magnitude of the electric flux, you're just going to use, in this case, can't use Gauss's law. And you don't have to do an integral because it's all uniform and simple. It's just going to be EA cosine theta. And notice when the field goes up and the area faces down, the cosine of theta is going to be 180, right, on the bottom. The bottom's facing down, the field is going up. It's a cosine of 180, which is a -1. So you get a negative flux. Negative flux means the flux is entering. If you were to do it at the top, the field faces up. The field lines come out up. It would be the cosine of 0. Remember, an area element, the direction is always normal to the surface. Don't get that wrong. Perpendicular to the surface. The area vector of the bottom is a normal to the surface. It points down. That's an important concept to get. So you do have to calculate the area. You need to put it into meters squared. This is already in the right units. And I leave it to you to do the calculation. So read this carefully. In this case, the cube is going to be rotated 45 degrees about the x-axis. So the x-axis is the axis. You're going to rotate it this way, 45 degrees. The field is still going up. So you want to draw yourself a figure for that. So this is what you should visualize. This is the bottom of the cube rotated. So now when it goes through, it doesn't go through a flat surface. It goes through two faces. Remember, it's three-dimensional. Two faces that are 45 degrees to the field. So the flux through this plus the flux through this is going to be, can you write the equation for that? So flux EA cosine theta, E is given, BA, calculate it in meters squared, and the angle between the E and the A, remember the A is facing this way, the field is going that way, is 45 degrees. Well, it's actually, it's going to be negative anyway because it's entering. That's just one face though. So to get the total flux, you have to take this value of one face and multiply by 2 because both sides are at 45 degrees to the same uniform electric field. And that will give you the flux which enters the cube. So 7, 8, and 9 are all related . 10 too, I guess. Conductors in static equilibrium. So let's talk a little bit about that. There is a set of properties that you need to learn for conductors in static equilibrium. There are 5 elements, I think, to that, and there are actually 2 videos on this. So before you do these problems, you might go and watch those videos. But let me just review that here with you now. So I will go over this quickly, and you should watch the video because I'm going to do this fast. But first, the electric field inside a conductor has to be 0. And the reason is, if the electric field inside a conductor weren't 0, the free electrons inside the conductor would move, right? If there were an electric field going through a conductor, then the free electrons would have force on them and they'd move. So the electric field inside a conductor is always 0. There can be no net charge inside a conductor. There can be charge in a conductor, but it all has to be paired off and canceled out. There can be no net charge because if there were a net charge inside a conductor, then there would be electric field lines and charges would move. And so what happens automatically in static equilibrium is any excess charge has to be on the surface of the conductor. And the field, so there's no field in the conductor, but the excess charge will be on the surface. The electric field lines leaving the surface have to be perpendicular to the surface. Otherwise, charges would be moving along the surface. And finally, the electric field on a conductor is going to be inversely proportional to the radius of curvature of the conductor at any point. So what does that mean? That means that if you have a conductor and there are sharp points, the charge at those sharp points will be more densely arranged. And so you should look at some figures and listen to the video to understand this one. It won't apply to this situation because it's all uniform curvature. Okay, so read it over carefully before we start. So anyway, it gives the dimensions of everything, and the outer ring or shell is a conductor, and that inner sphere is a conductor. And the inner solid sphere is given a net charge of 26 nanocoulombs. So if I were going to draw this carefully, I would put all that excess charge on the surface, and I would probably draw 26 I don't want to try and do that, positive charges around the surface of this sphere because they have to go to the surface. And then I would draw 26 field lines going out. The field lines can't go in because there can't be any field inside the electrics. There can't be any excess charge or any electric field inside the conductor by definition, because otherwise it wouldn't be in equilibrium. Charge would move. But this field line that leaves the inner sphere and gets to the shell can't go through the shell, because if it goes through the shell, an electron's going to move, and where's it going to move? It's going to move to the surface and terminate the line. So all these lines are going to go to the surface and terminate, and so what that means is that if there's 26 positive charges here, they have to be, no matter what's on this shell, they have to be, no questions asked, 26 negative charges on the inner surface here that terminate the field lines, because there can't be any field lines inside. Okay, where did those 26 negative charges come from? If the shell were neutral, that would leave behind 26 positive charges, which would then have to go to the outer surface. But what we see is that there are 13 negative charges, but we need 26. So we took 26, we took the 13. There have to be, we have to get 13 from the conductor itself, right? We take the excess 13, then we need 13 more. Why? Because all of these lines have to terminate. Why? Because the field can't go through the shell. So, without making it too complicated, that means we had to borrow 13 negative charges. That leaves 13 positive charges left over, and they can't stay inside the conductor. They have to go to the shell. So on the outside of the shell, I have 13 positive charges and 13 field lines going out. And when you add it all up, it makes sense, because the total charge inside here is a positive 26 and a negative 13. And when you add those together, you get a positive 13, and that's what we have. So outside of the sphere, we see 13 field lines, because what's inside of here, or any place outside, is a net charge of positive 13. Do you see how all that's logical? You say, whoa, my brain is fried. Okay, well, you just have to practice, and it will help if you watch the videos. So anyway, you got to do some calculations and then go through this choice of possible correct and incorrect answers. Remember, the field inside here is going to be 0. The field in this area is going to be the field of the same as if a point charge of 26 is in the middle. And if you're in the shell, the field is 0 because you're in a conductor. And if you're out here, the field will be the same as what? A point charge of 13 located at the center of that inner sphere. Let me just do one more drawing to emphasize that point. This is my attempt to show if you have 13 charges on the surface, the field is going to look like this. And if you have 13 charges as a point charge, the field looks like this. And if you draw a circle of this side out here, so if you're outside and you can't see in, you cannot tell whether this is a sphere with 13 charges on the surface or a point charge with 13 charges at the point. And so to calculate the field here, you simply take what you're really doing is this. You're using this equation where r is the distance from the center to where you're calculating the field, whether it's here or here. Once you're out here, the charge inside is 13, and so the K will be, the K is K, the Q is the 13, and the R will be the distance to where you are. And notice that if you're in the conductor, the net charge inside this is a positive 26 and a negative 26. So the net charge inside is 0. And so there's no field through this surface, which goes through the conducting surface, where there is no field. Wow, that's a lot of information. Okay, in this case, the inner solid sphere has 22 nanocoulombs, so put 22 positive charges here. That means 22 negative charges here. Why? Because the field lines, the 22 field lines have to terminate. They can't go through. So you put 22 negative charges there. But what do we have? The outer shell has 32. So we have 22 here. That's determined by this 22. That means there's 10 left over. And so you have a net charge of negative 10 on the surface. Remember, it has to be on the surface. And so the total charge inside is 32, negative 32. 22, that's a negative 10. That's what we see on the outer surface. And so the field outside here, anywhere outside here, will behave as if a point charge of negative 10 were at the center. And the field in here will be 0, and the field in here will be 0, but the field in here will be the same as a point charge of 22 at the center. And you just use that same equation that I erased, the EKQ over R squared. Do the calculations, and then you can answer the, choose the correct multiple choice questions. Okay, statements about conductors in static equilibrium. We got to move along. I'll let you do that. Statements regarding conductors and electric fields. More of what I talked about. Watch the videos if you need to. Let's go to number 11. Okay, so there's a charge inside, and the flux, we know the flux is going to be the same through all surfaces because the charge inside is the same and the number of field lines is the same. And this is very much like the earlier problems. You can use Gauss's law to calculate what the flux is, and then you can answer the questions. And here we have 3 figures. This is a negative charge, right? Whoops. Because the lines are going in. This is a negative charge because the lines are going in. This is a positive charge, same number of lines. So this is an equal positive and equal negative. And this, if it's twice as many lines, is twice as big. All that stuff we've been learning. Let's keep going. Answer those questions. 13. A number of questions about the cube. It's a negative charge. The field lines are going in. The flux through all closed surfaces are the same. All right. Let's go ahead to 14. So, number 14. Try doing this before you listen to me. See what you can come up with. So first of all, the net charge inside is 0. If you count the field lines leaving and the field lines entering, they're going to be equal. And the faces here, you can see what? 1, 2, 3 field lines leave, 1, 2, 3 field lines go in, so the net flux through this face is 0. But here, 1, 2, 3, 4, 5, 6, 7 field lines leave, and here 7 field lines enter. So there's a net flux out of here and an equal net flux in here. And you can get an estimate of what that is given the numbers and given the proportion of the lines. So for this one, it's important that you can visualize what the field around a long charged rod looks like. The field lines go out from the rod. Looking down the axis of the rod, you would see something that looks like a point charge. The field lines are spreading out in all different directions. This would be like a, I don't know, like a pipe brush or something. But if you look along this angle, the field lines are all going straight away from the rod, right? They're either going down or up or coming out toward us. But from this angle, the field lines look uniform. So what that leads to the conclusion is that no field lines pass through the ends of this cylinder. But the field lines that pass through the external part of the cylinder go through normal to the surface. And so the flux through the ends is going to be 0 because no field lines go that way, because no field lines are going in that direction. And the flux through the can depends on the area of the can and the field going through the surface of the can. And you see the cosine of theta, it's going to always be 0 because the field lines go out normal to the surface. And so the area of the can, take your cylinder, cut it, and unroll it, and you'll get a rectangle. And the rectangle has a length of L, and the width of the rectangle, right, the can that you cut and flattened out, is the circumference of the circle, 2 pi r. So that's how you get the area of the can. And let's see what else. So according to Gauss's law, the flux through the can will be the charge inside. And the charge inside is going to be the charge per unit length times the length that's inside. That is the length of the can. So if you multiply the length of the can by the charge density, I hope you can see that, you're going to get the total charge inside. And so the flux then, by Gauss's law, has to be Q inside over epsilon naught, right? And if the can is bigger, the same number of field lines, just like we saw earlier, the same number of field lines go through. Why? Because they all go through, and because the charge inside is the same, just like so many problems we saw earlier. So 16 looks like a lot of the ones we've done before. Gauss's law, right? The same flux through any closed surface. If it's a cube, then there's 6 faces. I'm going to leave you to that one. So number 17 is all trig. So the base is a square. That should be easy to get. The area of one of the sides, you know how to get the area of a triangle? You have to use that equation. And the base of the triangle is just one of the sides you're given, but the height you got to get. And that's trig, right? You get an equilateral triangle, you got to get this. Those are going to be 30 degrees. These are going to be 60 degrees. It splits here, S over 2. This is S. You can use the Pythagorean theorem. There's any number of ways to do it to get the height. And then you take 1/2 the base times the height and you get the area. So that's trig. And the distance from the origin to the apex, you got to draw that. So see if you can follow this. I'm going to cut this. I'm going to slice it with a knife right down here along these two lines and right across the diagonal. So I cut this in half. And then when I look at the flat half, I see this side and that back side, S and S, and I see the diagonal is the base. So if this is S, the diagonal is the square root of 2 times S. And so from the center of the diagonal to the height, that's the height from the base to from the origin to the apex. And so you've got your S, you've got your square root of 2 over 2S, this, right? And so once again, you can get that height. Or you can do it, no, I don't think you want to do it by angle, because I'm not sure what that angle is. I would do it that way. Okay. So this is a lot like the problems we did earlier. The field is going up. So it's going into the base. And it's going in normal to the surface. So it'll be the cosine of 180 and -1 because it's entering. And the area is just S squared. And the field is given. And the S is given. Make sure you put it in meters. And then to get the field coming out through these faces, if you try to do that by trig, it's going to be a little complicated. But since the field lines that go in all come out, and by symmetry, if the flux going in is 100, what does it comes out of? 4 faces. So it has to be equal coming out of each face. So 1/4 of the flux in will be the flux out through each face. Okay, this one's a little more complicated because this is your x-axis, this is your z-axis, that's your y-axis. And if the x-axis is along the diagonal and the field is along x, then the flux is going to be going through these two faces. And it's easy enough to get the area, we get the field, but to get that angle is going to be a little challenging. You can try it, but the better thing to do is to slice this down the middle. And if we slice it down the middle, then the field is going to go through, straight through, normal to the surface, that triangle that we described earlier. I hope you can visualize this, but if I slice that down along the two sides, I get a triangle which is S, S, and the square root of 2S, right? That's the diagonal. And then the field is going to be normal to that. So all you got to do is get the area of this, which we got the height, right? We calculated that. We have the base. We have the height. We get the area. We have the field. And because of this, it's normal to the surface. The angle is going to be 0 degrees. So the flux going through here is evenly distributed between these two sides, right? Because the flux enters through two sides, passes through this triangle, and then passes out the other two sides. I hope your brain can handle that. So this looks pretty straightforward. Everything lines up. You have all the values. I'm going to assume you can do this one. And now you have the field going up through a hemisphere. So the first field is, k hat. So that's going up. And so that just enters, like the hemisphere is a circle, right? So you just get the area of the circle times the field. It's going in. That'll give you the flux. and then it comes out of the sphere. By calculus, it would be a complicated problem. But since we know the field in has to equal the field out, we don't have to do that integral. We can just say the field in equals the field out, and the field leaving has to be equal to the field entering. But now if we put it along j hat, now we have the field going in through a curved surface and coming out through a curved surface. So what are we going to do? We're going to do what we did in the last one. We're going to slice the hemisphere in half along, since this is along j, we're going to slice it along the x-axis. And when you slice a hemisphere, what do you get? You get a half circle. And that half circle where you sliced it, I don't know how to draw the slice, forget about it, is normal to the surface. So you can just do EA cosine theta, and so the flux entering will be equal to the flux leaving, and without doing an integral, you can just do EA cosine theta for that half circle. So that's another tricky visualization. Okay, the key to doing this one is surround this charge by cubes. So imagine another cube over here, and another cube in front of this one, another cube in front of that one, and imagine how many cubes it will take to completely surround that charge. And then you can make the assumption that all the electric flux, the Q inside over epsilon naught, passes out, if you can get the symmetry, passes out equally through every cube. By symmetry, it'll pass equally through every cube. Then you have to decide how many faces. So this is touching this face, and this bottom face, right? It's touching those, and so it has to pass through those three, and it has to pass out of the other three. So, wow, it's hard to visualize, I know. Let me draw something. So you see this cube that I drew? Now, what I need is, I still have this exposed, right? So I need another two out front coming out of the screen. This one coming out of the screen. And then I have 4 cubes, but I've still only covered the top half of the charge, right? So those 4 cubes, if you can visualize the 2 that are coming out this way, right? The other one coming out this way. And then the one that fits into this space here, right? I'm messing up now, but like that. So there's 4, so there has to be 8 cubes. I'm giving you the answer to completely surround that charge. And when you look at the corner of a cube, you're going to see, you can picture, when you look at the corner, you see 3 faces. So the flux goes in through those 3 faces, which means it comes out through 3 faces. So 1/8 of the flux goes through this cube, but it comes out through 3 faces. So what's that? That's 1/8 times 1/3 through any one face. It's 1/24 of the flux. You have the answer. Can you picture it? I hope so. Okay, table of contents. Okay, there it is, table of contents, just in case you're looking for a specific problem and you don't want to have to fumble through the video. There they are. Good luck.